Hi everyone. In this video, we are going to discuss problem number 96, unique binary search trees from Leetcode. And it's a medium level problem. So the problem description goes like this. Given an integer n, the input given is an integer. No nodes or roots or nothing is given, just an integer is given. Given an integer n, we need to return the number of structurally unique BSTs, which stands for binary search trees, and the nodes of this BST are the numbers, the node values are numbers ranging from 1 to n. For example, if the given input is 10, then we have to create a BST, a binary search tree, which has got exactly 10 nodes, and the values of those 10 nodes are numbers ranging from 1 to 10. Now, with these 10 nodes, how many structurally unique BSTs we can form is the question. Okay, so they have given just 2 examples, and these 2 examples are not enough to understand properly. So in a while, we will head over to the whiteboard to see more examples and understand this problem better. Okay, so what is the first example given? The input is n is equal to 3 and the output is 5. So these are the 5 structurally unique BSTs we can form having exactly 3 nodes, and the node values are the numbers ranging from 1 to 3, right? I'll explain that later. And another example is if the input is 1, if the given integer is 1, then the number of structurally unique BSTs that we can form is 1, right? So I want you to pause the video here and come up with your own solution, because it's a very, very interesting problem. I want you to give it a shot before checking the solution. So now let's head over to the whiteboard, and first let's try to understand the question with examples. Let's see more and more examples, and then we'll try to devise an algorithm based on whatever is the pattern that we have seen in these examples, right? Okay, check this. If the given integer is 1, if the given input is 1, then we have to form a BST with only one node, and the value of that only node is 1. So how many such BSTs we can form? Oh, by the way, what is a binary search tree? It's basically a binary tree which is having the BST property. So what's the property? For every single node, all its left subtree nodes will have value less than the node value, and all its right subtree nodes will have value greater than the node value, right? So that is the BST property. So we will have to always maintain that particular property. Maintaining that property, how many such BSTs we can form? Okay, so when the given integer is 1, this is pretty obvious. That's it. There should be only one node, and that node's value is 1, and that is all we can do. There is no other possible BST that we can form. Okay, so this is one example. What is the answer? How many BSTs we could form if the given integer is 1? It's only one BST, right? We can form only one BST. Fine. If the given integer is 2, so we need to create BSTs having exactly 2 nodes, and the node values are 1 and 2. Okay, so there are 2 possible ways we can do it. If the root node is 1, then the only other node, which is the node having value 2, should be the right child of this node, because we have to maintain the BST property. The elements in the right subtree must have value greater than the node value itself, right? So this is one way we can form a BST. Or if you choose the root node as 2, the only other node is node with value 1, and it has to be in the left subtree, again, to maintain the BST property. So except for these 2, there is no other possible way of forming any other BST having exactly these 2 nodes, right? So how many BSTs we are able to form here? In this case, it is 2 BSTs. Fine. So let's see more examples so that you will get proper idea about this concept, right? Now check this. If the given integer is 3, Now we have three possible options for the root node. One is the root node can be 1, or the root node can be 2, or the root node can be 3, right? If the root node is 1, the remaining nodes are 2 and 3. And both of them will go to the right subtree only, right? It can go to the right subtree only because we have to maintain the BST property. But it can go to the right subtree in two different ways. Listen, we are converting this problem into sub-problems, right? I'm fixing the root node, that is 1 only, right? But the other two nodes are 2 and 3, right? So how many different ways you can form subtrees with the nodes 2 and 3? It can be 2 and 3 like this, or with the same root node 1, it can be 3 and 2. Do you see that? This is a sub-problem. This is a sub-problem of this main problem, right? Now keeping 2 as the root node, how many different BSTs we can form? 1 must definitely go here, and 3 must definitely go here in order to form BSTs. And this is the only way of forming a BST, having 2 as the root node, okay? So when we keep 3 as the root node, what happens? The other two nodes, 1 and 2, should go to the left subtree. And these are the following ways it can go to the left subtree, right? Or the other way is, again, as you can clearly see, these two are sub-problems. So we are breaking down a given problem into its sub-problems. And we are solving the sub-problems. And based on that, we are going to get the solution for the main problem, right? So this clearly tells us that this is a DP problem. We will have to use the concept of dynamic programming. And how many different BSTs we formed here? 5. Now, what if the given integer is n? What if the given integer is n? Now, how many different options do we have for the root node? The root node can be 1, or the root node can be 2, or the root node can be 3. It goes on up to the root node can be n, right? If the root node is 1, the remaining n minus 1 numbers, 2, 3, 4, all the way till n, the remaining n minus 1 numbers, they all should be part of the right subtree, because all these numbers are greater than 1. So all these remaining n minus 1 numbers will go here, and nothing goes here. So this is empty. Nothing goes here to the left subtree. Okay. So this is basically the question of how many BSTs you can form with 0 nodes, and how many BSTs you can form with n minus 1 nodes. Make sense? It's basically how many BSTs you can form with no node, and how many BSTs we can form with n minus 1 number of nodes, and those node values are 2, 3, 4, so on up to n. Okay. If we choose 2 as our root node, then 1 will go here, and the remaining n minus 2 numbers, what are they? The numbers greater than 2, 3, 4, 5, all the way till n. These n minus 2 numbers will go here, right? So again, this is the question of how many BSTs we can form with just one node times how many BSTs we can form with these n minus 2 nodes, right? Okay, what about this? What if we choose 3 as our root node? 1 and 2 will go here, again to maintain the BST property, and the remaining n minus 3 numbers, okay, those n minus 3 nodes, 4, 5, so on up to n, will go here. Once again, what is this? It's a question of how many ways you can form BST using these two nodes times how many ways you can form BST using these n minus 3 nodes, right? And we will have to take the product of these two, right? It goes on and on, right? And the last case is where we choose the last number as our root node, right? And all of the numbers, the remaining n minus 1 numbers which are 1, 2, 3, so on up to n minus 1, all these numbers are less than n. So they all will go to the left subtree. To the right subtree, we have absolutely nothing. Okay. So it is once again the question of how many ways we can form BSTs using these n minus 1 nodes, and how many ways we can form BST using no node, 0 nodes, right? You see, we have seen in the previous example, if only one node is given, we can form only one BST. If two nodes are given, 2 BSTs. If 3 nodes are given, 5 BSTs. What if no node is given? No node is given. Then how many BSTs we can form? That is again one BST, because with that non-existing node, you cannot form any BST at all. And there is only one way you cannot form a BST, right? So the answer is 1, right? Even if 0 nodes are given, you can form only one BST, that is to not form any BST. There is only one way you can do it, right? Now, how do we express this as a mathematical function? And later on, we will write it like a proper, we'll convert that, we'll translate that into a proper algorithm, right? So what's the main problem we were trying to solve? The given integers n, so it means we have n number of nodes, 1, 2, 3, so on up to n, there are n number of nodes, okay? How many different structurally unique BSTs we can form? So we have broken down this problem into sub-problems, okay? So if you keep the root node as 1, you can have BST 0 times BST n minus 1 number of structurally unique BSTs. If you take the root node as 2, you can have BST of 1 times of BST of n minus 2 number of structurally unique BSTs. If you take root node as 3, you can have BST 2 times BST of n minus 3 number of structurally unique BSTs, all the way till the last option, which is if you take the root node as n, then you can have BST of n minus 1 times of BST of 0 number of structurally unique BSTs. So how do we write this? Mathematically, you can express it as follows. Then we'll convert that into a algorithm. Okay. So BST of n is what is it? Sigma r ranging from 0 to n minus 1 of, this is BST of r. It will make sense. I'll explain. BST of r times BST of n minus 1 minus r. Okay. So sigma stands for summation. You put r is equal to 0. This is BST of 0 times BST of n minus 1 minus 0 is n minus 1. Yeah, it matches. Okay. If you put r is equal to 1, the next number, if you put r is equal to 1, it's BST of 1 times BST of n minus 1 is n minus 2. Again, it matches. Put r is equal to 2 here. It's BST of 2 times BST of n minus 1 minus 2, which is n minus 3. It matches. All the way till the last option is what? Put r is equal to n minus 1 here. In the place of r, you put n minus 1. It is BST of n minus 1 times BST of n minus 1 minus of n minus 1 is BST of 0. Okay. So this entire thing is represented as follows. It's very clearly a dynamic programming problem, right? It's clearly a dynamic programming problem, and we can expect our, in this case at least, we can expect our algorithm to be a recursive one, right? And there is a very, very serious issue here. This is going to be recursive. That by itself is not a problem. But if you call the function once, for example, just for example's sake, consider this. I want to find BST of 10, let's say, which is not a very big number, just 10, right? So what is BST of 10? It is, according to this formula, it is going to be BST of 0 times BST of 9 plus BST of 1 times BST of 8, all the way till BST of 9 times BST of 0. So the function is calling itself within the function, therefore it is recursive. Okay. And on top of that, if I have to find BST of 10, I will have to call the BST function how many times? 1, 2. In the first term, we are calling it twice. In the second term, we are calling it twice. In the third term, we are calling it twice. All the way till the last term, we are calling it twice. So just to find BST of 10, in the first call itself, we will have to call BST 20 times. So if I have to find BST of 9, then you can guess that it is going to be 18 times. If I have to find BST of 8, you will have to call BST in the first recursion itself. In the first call itself, you will have to call BST 16 times. It goes on, right? We don't have to calculate the exact number, which is super complicated, but we know for sure that it's at the very least, it is going to be at least a factorial. Okay, it is going to run in factorial time complexity. And this is a perfect recipe for disaster. So this is where we are going to use the concept of caching and memoization. So you know what is memoization? So whenever we are calling a function on certain input, the function is computing the value and it is giving us some corresponding output, and we are going to store that value. We are going to store that value for future function calls for the same input, the recurring input. Instead of computing the function once again, we are going to simply return the stored value. So that way we can save a lot of time. Otherwise, it is going to be a very, very expensive function call, right? We definitely want to avoid this. Okay, so this is how we are going to code it out. First, let us start with cache, which is going to be a hash table. In Python, we are going to use the dictionary. And for at least the first 1 or 2 values of the given integer, let's directly write the answer because it's not a big deal. If the given integer is 0, we know that the output is going to be 1. If the given integer is 1, again, the output is going to be 1. That much is enough. Okay, so that is going to act like the base case. It's not exactly the base case, but kind of, yeah. Now we are defining a function BST, which is going to give us the number of structurally unique binary search trees for the given integer n. So we are defining BST of n. We're defining BST of n as follows. So the first thing that we're going to do is we have to check if the given input n is in cache. Because if it's already in cache, let's say if it's already in cache, we don't want to, compute this function once again. We don't want to apply this function. We want to avoid it. We want to directly, return the stored value, right? And we are going to actually apply the function only when this input is not found in the cache. In that case, of course, you will definitely have to apply this function. So if n is not in cache, then what are we going to do? Let's have a variable, okay, to denote the sum, the sigma. Let's have a variable to denote the sum. Its initial value be 0, right? Then we are going to create a for loop for r in the range of, it's ranging from 0 to n minus 1, right? So I'll put range of n. You know how the generator works in Python. So when you put range of n, it starts from 0 all the way till the number excluding n. So it will go all the way till n minus 1. So 0 to n minus 1 is taken care of by this generator function. Okay, so for r in the range of n, what are we going to do? We are going to add sum is equal to sum plus of, we're going to add what? BST of r times BST of n minus 1 minus r, right? And then we are going to return. Oh no, we're not going to return. No, we're not going to return. We're going to cache it. Right, like I told you, we are going to cache it. Then cache of n is the value of the sum. And finally, we are going to return cache of n. So before throwing out the output, make sure that the output is stored as in that particular dictionary. Okay, so for this particular input, the output is this number. Let's store it, then return the value, so that in future references, in future calls for the same input, we can just like that get the answer. We can bypass this whole thing. That if statement, as you can clearly see, we can bypass this entire thing. We can just directly get the answer if at all the same input is repeated sometime in future, right? So this is our code. So now we will have to call this function, okay, BST of n, and return the value. Okay, then now let's go back to Leetcode and we'll just code out the algorithm and see how it works. Let's change it to Python 3. Okay. So what's the first thing we're going to do? We are going to initialize a cache in the form of Python dictionary. So for 0 key, the value is 1. For key 1, the value is 1. Okay. And then we are going to define this function bst of n. The first thing we are going to see is if n is in cache or not. Only if n is not in cache, only then we will actually apply the function. Okay. Otherwise, we'll simply return the cache value, the stored value we will simply return. Okay. But if the value is not present in the cache, what are we going to do? Okay. In that case, we are going to create a variable called sum, and we are going to run a for loop for r in range of n. You're going to add sum is equal to sum plus of bst of r times bst of n minus r minus n minus 1 minus r. Okay. Then we are going to store the value. Cache of n is some value. Then we'll return the sum. That's it. Okay. Now let's call this function outside of the definition. Return bst of n. Let's dry run this and check if it's working. Yeah, it's working absolutely fine. So let's actually submit our code. Let's now run our code and see if it's doing well in all the test cases, if it's clearing all the test cases. It's doing absolutely fine. Okay, then I hope you found this particular solution helpful. Thank you.